So everybody should be able to hear us now. We're just getting started. So thank you for your patience. So I would like to welcome Saakshi Dulani from the University of Geneva, who's going to be talking today about entry guide.
Hi, everyone. Thanks so much for having me. So this presentation is based on my dissertation research, and I decided to take a deep dive into the black hole information loss paradox. So there are several questions that are informing what I'm going to be talking about today. I won't be able to go into everything I'd love to in depth, but I'll give you a bit of background as to what motivated this line of inquiry. So, there are so many proposals out there in the discourse, and it seems like there's really cacophony as to what the paradox is supposed to be about. You hear the standard story that we have non-unitary evolution, so somehow indeterminism is supposed to be paradoxical. That doesn't sound quite so compelling. And then you have people in the field that say, no, we don't even have to wait until the black hole fully evaporates to find a problem. And they've recast it in terms of what's called the page time paradox, or now what's more popularly known as firewalls. And then, of course, there's just so much disagreement over what a good proposal looks like. And so what I wanted to do is basically get the lay of the land and integrate all of these positions into a framework so that we understand at what point people are coming in with their positions. And in doing so, I realized that I retroactively fleshed out Page's early intuitions, that the paradox doesn't really have to do with the nature of laws, but it actually has to do with what I call phantom entanglement. So I'm going to very briefly set that up for you so that we can just see how resolutions to my conception of the paradox very naturally bring in the interpretation of black hole entropy as perhaps the key to unlock this puzzle. Now I can...
You should probably click on the slides and then yes.
There we go. So my goal is to come up with a unified framework for what's actually a family of puzzles. And so one of the things that I want to accomplish is introducing a taxonomy that integrates the debates between black hole thermodynamics and information loss. And then my second goal is to argue that we don't need to wait for a final theory of quantum gravity to coherently pose what the paradox might be. And in fact, we can use a lot of work done in the philosophical literature on guiding principles for quantum gravity approaches to actually formulate what the premises might be that we want to be satisfied in order to decisively say there's no longer a paradox. And then my final and most important goal is to show that when Bekenstein-Hawking entropy is explicitly acknowledged as a guiding mathematical principle, then it can also be used to evaluate the proposals. So first, I'm going to talk a little bit about why we might think that black holes are universal thermodynamic systems. And then I'm going to introduce my framework of phantom entanglement, the solution of which is going to select the guiding principles that have anyways been acknowledged as being very fruitful for quantum gravity research. And then I'm going to suggest what the premises might be for us to evaluate whether or not black hole information loss has been resolved in its contemporary form. So, fast forwarding from when Hawking first put forth what the puzzle might be, now in quantum gravity, do we still have a paradox? And then finally, I'm going to add the desideratum that will form what I call the holistic desiderata, where we really want to narrow down and vet the proposal space. Okay. So I'm sure a lot of you are already familiar with this since we're in the Black Hole Initiative, but just so that we're on the same page, let me just summarize at least Hawking's derivation of radiation and black hole evaporation, because by now there are so many. So we start with quantum field theory on curved spacetime. And what we have on the left-hand side of the semi-classical Einstein field equation is a classical geometry of a vacuum black hole solution. And then on the right-hand side, we have quantum matter fields, particularly the expectation value of the stress energy tensor, also satisfying vacuum conditions. So of course, both sides need to match. Now, he didn't explicitly need the equation, but to make sense of why black holes evaporate, we are ultimately going to need mutual coupling. So this seems very boring, but it's actually an interesting universe, because by decomposing the quantum matter fields into positive and negative frequencies, we get some very insightful heuristics. We can think of these fields as containing entangled virtual particles with positive and negative energies that cancel each other out. So the expectation value basically recovers the vacuum. And what Hawking realized is that we start off with an initial global state that's pure and it precludes further particle annihilation. So it's the standard definition of a vacuum. But what's different is that the event horizon is now a causal barrier separating the members of these Hawking pairs. So presuming that the speed of light barrier can't be exceeded, what happens is that the negative energy partners get trapped in the black hole, and the positive energy partners escape to infinity. And then what we're left with is a final global state that is no longer a vacuum, and we actually have black body radiation that obeys the no-hair theorem. So the no-hair theorem basically says that black holes, no matter what the collapsing matter was that formed them, by the time they settle into a stationary state, they're going to have just mass, electric charge, and angular momentum. And since this radiation in some sense is produced at the event horizon, that's the maximum amount of information that it's going to contain. But what's telling is that this final global state is mixed, and it looks exactly thermal. So here's just a schematic of how we can, again, it's a heuristic, but visualize what might be going on as we have these Hawking pairs. The negative energy partners get trapped in the black hole, and then the positive energy partners manage to escape. So why might this make us have more credence in black hole thermodynamics? Well, Hawking radiation has a temperature, and it turns out to be inversely proportional to the black hole mass. And we actually notice a remarkable correspondence between the first law of black hole thermodynamics and Clausius's theorem. So if we plug that temperature in, we can solve for black hole entropy. Well, technically, it's the entropy that has been gained by the radiation, but if we assume that they're in equilibrium with each other, we can also say that's the entropy lost by the black hole. And as we see, it is proportional to horizon area, which is going to be a key part of the puzzle and how we're going to use this quantity to tell us more about how we can solve information loss. So the key question is black hole thermodynamics physically salient? And there's a spectrum of philosophical positions, but if you bifurcate that spectrum into two umbrella camps, then I think it sheds a lot of light on the information loss debate. So the first camp is that it's simply a mathematical analogy. We shouldn't read too much into this. It's a mathematical analogy between geometric theorems and phenomenological laws. And it's also a kinematic, not a dynamical effect, because in Hawking's derivation, he basically used a special type of transformation to go from the initial state to the final state. And we don't really have any sense of what the mechanism is for how the black hole is radiating, and we don't even need to bring in energy conservation for there to be radiation. And then, of course, this is something that Eric has done a lot of work on, and I really liked his point that in the absence of an independent derivation in quantum gravity, black hole evaporation is put in by hand. You know, we see radiation, we're like, that energy has to come from somewhere, and so we surmise that there must be coupling between the geometry and the quantum matter field. But that is, again, based on an a priori expectation. There's another camp that invests in black hole thermodynamics, and their argument is that thermodynamic phenomena are multiply realized across diverse systems, and we think that black holes should be among them. So there's been some work, even classically, that maybe space-time physics is phenomenological, the way we think thermodynamics is. And Hawking himself acknowledged this in his inaugural paper, where you can have a sequence of these kinematic states to approximate dynamical evolution. And there have been subsequent calculations carried out that recover the back reaction. And then most importantly, black hole thermodynamics imbues force into the generalized second law. If we think we can't make perpetual motion machines, if we think that the arrow of time is something to be taken seriously, then black holes should not be able to violate the second law. And so we also look at what we think is thermodynamic entropy, and we notice an interesting congruence of constants. We have the speed of light, we have Planck's constant, we have Newton's gravitational constant. And so that together is a good hint that maybe black holes have underlying quantum gravitational degrees of freedom. So this was Hawking's expectation. It should not be thought unreasonable that a black hole, which is an excited state of the gravitational field, should decay quantumly. So at the outset, there was some foresight that this is simply, a promissory note, but ultimately it's going to have to be fulfilled by a theory of quantum gravity. So with that in mind,
Before we move on to the next section, I have a quick question.
Yeah.
So today there are different ways to derive the Bekenstein-Hawking entropy, to derive the Hawking evaporation effect, that are quicker, cleaner, but also seem conceptually somewhat different from the original Hawking calculation, which was based on these Bogoliubov transformations and so forth.
Exactly.
One that I particularly like is the partition function derivation.
Okay.
Where you calculate a quantum field theoretic partition function on a black hole spacetime, and you discover that you need to get a certain periodicity relation for the Euclidean time to get a consistent solution, and it exactly corresponds to there being a temperature that is exactly the Hawking temperature. Do you know how folks in Camp 1, the mathematical analogy camp, if this is just a mere analogy or it's not really thermodynamic, then why do we have these approaches where we're using the same tools that we use to calculate thermodynamic effects in quantum field theories, giving the same results?
Right.
Doesn't that add robustness to the physical claim and also some credibility to the idea that it is in fact a genuine thermodynamic statement?
So you're asking about the weight of consilience.
Yes, exactly.
Yeah.
Precisely right.
So I'm not aware of that particular derivation, but off the top of my head, my guess is if it's involving a partition function, the folks in Camp 1 tend to be skeptical of a subjective understanding of entropy in line of Shannon entropy. And so they're going to say that more work needs to be done to show me why I can derive Hawking temperature from that interpretation of entropy.
Fair.
Yeah.
I also think they don't like the fact that it's an Euclidean passage.
Well, yeah, I mean, anytime you're invoking a path integral in kind of a quantum field theory curve spacetime context, there's going to be some, I mean, the derivation is not totally rigorous, but it is highly suggestive, right? That you get the same answer from like a very different kind of approach. And it's not really that it's a different derivation, but the original derivation, right, is not an explicitly thermodynamic derivation, right? We have to, we're computing expectation values of particle numbers, and then we just take a leap and say, well, this looks like a thermal distribution. Whereas in the partition function approach, we're explicitly using a tool that we use to compute thermodynamic partition functions from which we regularly extract statements about things like temperature.
Right. And so,
Don't we usually do that in Lorentzian setting?
Yes.
So I think that's maybe what the people don't like, right? That is Euclidean.
I completely agree that it's not a rigorous derivation.
I like it.
Yeah, exactly. It's just, it could have given a completely different answer and it didn't, right?
Sure, but you could also have said, here, let me just do this random thing that gives the same answer. So if there's no clear connection in the way,
That's okay. No, but I mean, of course, the Wick rotation you do to go from a Lorentzian space-time to Euclidean space-time is exactly what we do whenever we compute we use a path integral approach to compute a partition function. So it's consistent with methods that we use in other parts of quantum mechanics, right? It's just a standard sort of Feynman Katz like Wick rotation trick. So I mean, yeah, the fact that we use this approach that works so well in other contexts and it gives the correct answer and it has this very explicitly thermodynamic tinge, to me is very compelling, and I haven't really seen it properly. Anyway.
Right. I mean, in the philosophy discourse, Wallace would very much agree with you. And the most I can say is there are other reasons where people might be skeptical about the Euclidean path integral approach, but to answer your question bearing on thermodynamics, they also just tend to be very skeptical of Gibbs entropy, which is what, you're using ensembles in that tradition.
Thank you.
Is the Unruh sort of take on this fit into one of those two camps?
It will actually come in later. So when I talk about the different interpretations of Bekenstein-Hawking entropy, one of those interpretations will very much want Hawking radiation to be an extension of Unruh radiation. Yeah. So what I found really interesting is that Susskind and his collaborators, Susskind being one of the foremost champions of information conservation, hedged his bet despite the fact that he put so much effort into trying to come up with an alternative framework. We conclude that the information paradox can only be precisely formulated in the context of a complete theory of quantum gravity. I call this the grown-up answer. I think it's facetious and it's not transparent about the work that's going into actually developing quantum gravity in order to solve this problem. And I also think there's an underlying pretense that Hawking's semi-classical framework is an unsuitable target of analysis. I mean, as Jacob pointed out, it's not very rigorous. There are a lot of imprecise and unproven assumptions that go into it, some shortcuts and approximations. But my attitude is this: if a critical assessment of the puzzle yields a genuine paradox, then we have an actionable prescription for quantum gravity. So I think the best case scenario is to see exactly which, imprecise and unproven assumptions contradict each other, and then we can use that to actually have a definitive benchmark to evaluate the plethora of proposals which claim that they've either solved or are on their way to solving it. So here is the Penrose diagram that Hawking put forth. I've annotated it just to make it visually clear how the Hawking pairs fit in. Is everyone here comfortable with the Penrose diagram? Can I just breeze through this? So what I've done is I've indicated in red trajectories of the positive energy partners and in blue trajectories of the negative energy partners whose world lines end at the singularity. And if you see from sigma 1 to sigma 3, we've actually lost the blue trajectories, which means we have a change in degrees of freedom from sigma 1 to sigma 3. So these two states do not live in the same Hilbert space. And moreover, the decisive feature of these Hawking pairs is their monogamous entanglement. And it's highly suggestive that the reason the final state that Hawking calculated is mixed is because these positive energy partners are still entangled. And this is, physically unintelligible situation because how can a physical system be entangled with something that, is no longer on the same state, especially when entanglement is a feature of a pure state, right? Presumably there should be some global state that accounts for these correlations. So what we have is that Hawking radiation is an entangled global system. That's an oxymoron. And as I just mentioned, and I can go through this very quickly, entanglement is a property of pure states, and I'm interpreting it as a physical relation between subsystems. And of course, a state usually relies on a metrical determination of simultaneity. We think that the final thermal state, especially in quantum field theory, thermality indicates that if you're thermodynamically coupled with your environment, you're also entangled with your environment. We want to know where the negative energy partners are. But of course, another entangled subsystem to purify the Hawking radiation is nowhere to be found on sigma 3. Because no matter how we carve up the space-time, the singularity has basically cut the world lines of the negative energy partners short. And so I think a metaphor might be, if anyone has seen Star Trek, there are these aliens called binars that are genetically bonded to each other for life. So, that's one way to think of entanglement. And the contradiction is that Hawking radiation is both a global system and entangled subsystem. And of course, these two things are mutually exclusive. And that is why I call it the paradox of phantom entanglement, because it seems like the complementary entangled subsystem is nowhere to be found. And I realized retroactively that this is probably what Page had in mind when he was worried that the von Neumann entropy of Hawking radiation has been increasing without bound. But if the complementary entangled subsystem is supposed to be in the black hole's entropy is shrinking as it's evaporating. And at some point, it's going to be very apparent that the black hole simply is not large enough to store the entanglement with the Hawking radiation. So this, I think, is a much better conception of information loss because it uses von Neumann entropy, which is an information measure. There's no bias about whether we have deterministic or indeterministic dynamics. And I think we can come back to this in Q&A if anyone has any questions. So here's a quote again by Susskind, which is funny because he thought, we couldn't even pose the problem in the first place. And yet he says, all hell would break loose in all of physics, not just black hole physics, once the door to information loss was opened. And I agree with him, because physics is a theory about physical entities. We, of course, do not want to admit any phantom entities to explain what's going on. So now, what do we do with this? Semi-classical gravity clearly is invalid as it stands, at least the framework that Hawking proposed. But I also think that this is where looking at black hole thermodynamics is very useful, because why would you have an incentive to solve this paradox if you did not think that black hole thermodynamics was physically salient? So I really think that, if all it is a mathematical analogy, where we don't think Hawking temperature is truly temperature, if we don't think Bekenstein-Hawking entropy is truly entropy, then, at this point, we just, wash our hands of the problem and move on. But that's clearly not what has happened, given all of the proposals we see today. So Camp 1, I think, just has no business being in this debate because it disenfranchises the majority of responses.
I'm a little lost here.
Yeah.
So Page argument says information has to be lost, right? Because information is, I don't think it's thermodynamics. You can actually count
Yeah.
how many bits are missing here and
Yeah.
where could it possibly be.
Yeah.
And where it could possibly be is just not large enough
Right.
to hold this information.
Right.
Why would Camp 1 say that that is irrelevant?
Oh, then they would just say black holes don't radiate. They would just say the entire framework needs to be dispensed
Oh,
with.
good. No, that I'm fine with.
Yeah.
So they're saying that there is no Hawking radiation.
Exactly.
Okay,
Exactly.
fine.
Yes. don't know if I missed something, but anyway, this is the terrain of Camp 2, which is why it will really behoove us to pay attention to how these different proposals are making contact with the paradoxes I've laid out and what that says about the interpretation of black hole entropy. So maybe I can, just in the interest of time, just summarize that his calculation is definitely ill-suited after the black hole reaches Planck mass, maybe before. Camp 2 is the one that really bears the responsibility because it requires high energy quantum gravity, and most proposals, as we see, are coming out of those approaches. And then just to put that out there, it doesn't mean that quantum gravity can replace a semi-classical framework. We would still need to reverse engineer a modified framework of semi-classical gravity. It's going to require retroactive exegesis, but that's because thermodynamics is inherently a spatiotemporal discipline. Entropy is quantified through spatial boundary conditions. The second law hinges on temporal boundary conditions. So for the arguments that, we shouldn't really even care about semi-classical gravity because we need quantum gravity anyway, I don't find that persuasive. If we want continuity and universality between black holes and other thermodynamic systems, that obviously, those laws are applying in space-time. So Hawking, again, foresaw this. Presumably such a scheme would only be an approximation to a deeper theory still to be found in which space-time itself was quantized. So what will the modifications look like? Well, there are three regions. One, singularity resolution would definitely take care of the problem that when world lines are being ended prematurely. The final evaporation event, when the black hole is really small, could also be subject to novel physics because these are very small scales at very high energy. And the event horizon may also be subject to quantum gravitational modifications if we think that the no-hair theorem is just a coarse-grained description of the black hole, but in fact, every black hole is unique depending on how it was formed. So we have this contradiction, and what a solution entails is denying one or the other equality. So we can say that Hawking radiation is a global system, and we can say that Hawking radiation is a global system, and the proposals that do this include stretched horizons, so in the membrane paradigm, firewalls, soft hairs of the horizon, wormholes and islands, so the really recent work on entanglement wedge reconstruction. And what all of these proposals have in common is that they really focus on the event horizon to get information out. And they also use some notion of complementarity.
I have a question about the last item.
Yeah.
The last item, my understanding was that it regards it identifies a connection between entanglement and wormholes. So wouldn't that fall into the entangled subsystem category? I mean, because they're taking the entanglement seriously. They're just assuming that stuff in the black hole is actually local with stuff outside the black hole.
No, they're not saying it's local. So actually, they're using ADS CFT correspondence to talk about how you can reconstruct interior degrees of freedom. And so that's an interesting case. They'll say that the entanglement with the interior is a basis-dependent description. In another basis, you can find a dual description where you just have Hawking radiation left at the end, and it's the internal entanglement structure that's used to reconstruct the interior observables. Yeah. So the other way you can go is to say that no, Hawking radiation is truly an entangled subsystem. There's going to be a black hole remnant in some shape or form. And the types of remnants range from baby universes to the Minkowski space-time that you have at the end actually, again, is a coarse-grained description of underlying atoms of geometry. You can have stable Planckian remnants. You can have decaying remnants. For example, Ravelli recently came up with a proposal that black holes at Planck scale have a very high probability of tunneling into white holes. So all of those proposals basically, grab onto this horn of,
Doesn't, again, the page argument
Yeah.
basically say a stable remnant can't do it, it's just too small to hold all the entangled information.
so I will show you the curve, the entropy curves in a moment. So they say that Bekenstein-Hawking entropy does not bound black hole entropy. There are additional, in fact, it has to be unbounded interior degrees of freedom that are not participating in the thermodynamic interactions, but they are still entangling with the Hawking radiation.
Wow.
Yeah.
So the Planck fellow can
Yes.
hold as much as it wants.
Yes.
Okay?
Yes. Absolutely. So I think I can skip this because I've already much done that. And so now what we want to do is we want to find a way, I mean, those were just, that was just scratching the surface of the proposals that are out there. I think those get the most airtime, but we definitely want to, now be able to rule some out. And here are some proposed premises that a lot of work in philosophy is proving to be useful to articulate. So the main question is, without a final theory of quantum gravity, how do we pick the premises? And so there are guiding principles that are already pillars of quantum gravity. And I think, given this current state of affairs, it's a feature, not a bug, to keep the desiderata flexible and open to interpretation. Because if we try to go with premises that are too technical or precise, then I think it's very easy to dispute as unfaithfully representing the puzzle. So we don't want specific theorems or mathematical principles from prior theories. And what I have in mind are recent formulations of the paradox using global hyperbolicity or unitarity. I think that's just a red herring and the wrong way to go. Or the no cloning theorem. But of course, we don't want excessive manipulability as well, because then it would be vacuous. So we want to find premises in a Goldilocks. And I think this is the master guiding principle right here. Specifically, we assume that the origin of the thermodynamic behavior of the black hole is the coarse graining of a large, complex, ergodic, but conventionally quantum mechanical system. And I have rephrased this into what I call the universality argument, where black holes consist of Planckian degrees of freedom, whose aggregate statistical behavior recovers Bekenstein-Hawking entropy, which in turn reproduces universal thermodynamic phenomenology. And of course, there are details that need to be filled in. So what exactly counts as a universal thermodynamic behavior? Here are some examples. Black holes need to be able to mediate thermal contact. They need to be able to equilibrate with external systems, but also settle into equilibrium internally. Perhaps they can be used to implement a Carnot cycle. Of course, since we have calculated that Hawking radiation is thermal, it should exhibit the Planck spectrum. And when we talk about reducing thermodynamics to statistical mechanics, it should also fulfill preconditions for various statistical ensembles when they're applied. And one of the most interesting ones is the definition of thermality, which I mentioned in passing. In quantum field theory, thermality means that you're coupled to a heat bath or an external reservoir, not just thermodynamically, but most likely also via entanglement. So as a summary, here are the bare desiderata. I unfortunately don't have time to justify all the other ones, but the idea is that this is the master guiding principle. And then we have these other guiding principles that naturally fall out of it when we think about what we need this to do for us. So we have the universality argument. Of course, we need to say that black holes evaporate. I mean, that's what got us going in the first place. And it's going to be at least until reaching Planck mass. We want all global states to be informationally complete, so we don't want entangled global systems anymore. We need semi-classical gravity to be valid at most up to a Planck scale cutoff, and I had argued earlier why it's necessary to reverse engineer it precisely in service of UA. And then, of course, we need an empirical coherence condition. So, any time that we have predictions being made in overlapping domains, they need to reproduce whatever has been empirically confirmed. And this is related to a generalized correspondence principle where effective theories are recovered as limiting cases. So these guiding, especially 5 and 6 have already been used in quantum gravity. And now I want to show that they come very naturally from treating black holes as these universal thermodynamic systems. So the Beer desiderata are intertheoretical guiding principles that set thresholds for pursuit worthiness, and they're external constraints. So in the case of black holes, the most important external constraint is deriving the correct proportionality constant, which is 1/4 of the area to leading order, through microstate enumeration. And here's just a quote of how mathematical features can motivate the search for a new theory, and this has been perhaps the most important external constraint that people working in string theory and loop quantum gravity, the more mature approaches that can handle microstate enumeration for black holes, that they've taken themselves to be able to deliver. And, perhaps we can even think of them as means of non-empirical confirmation through meta-inductive reasoning. So this is also some work that has been contentious, but we need some way to explain how quantum gravity can still be viewed as science, properly speaking. Now, of course, the philosophical tension is, what does Bekenstein-Hawking entropy mean? And here's a quote from Wallace, which I think very perfectly captures the rivalry in the discourse. Remnants or thunderbolts or baby universes, no matter how helpful they may be in preserving unitarity, do nothing to preserve the statistical interpretation of black hole entropy or any account of black hole thermodynamics as arising from statistical mechanics in the ordinary way. So this quote explains why there are so many proposals and why we have not been able to come to an agreement on what we want out of a prospective solution. So once we get there, then we'll be able to have what I call the holistic desiderata. So the obvious difference between terrestrial systems and black holes is that the latter possess causal barriers, and how to cash out in the ordinary way is non-trivial. So one thing that I really like about the setup of the paradox is that choosing between late-time Hawking radiation as a global system versus as an entangled subsystem uncovers how CAMP2 quickly disintegrates into rival branches. And the main point of contention is the interpretation of Bekenstein-Hawking entropy, basically how much of the black hole does it account for? So the two ways of solving the paradox can be labeled into what I call Safehouse solutions. So these are the remnants. The black holes, serves as a safe house to store the entanglement, and they're going to have an interpretation of causal entropy. On the contrary, what I call evacuation solutions, basically radiation at the end, is the only thing that's left. They're going to or a holographic interpretation of Bekenstein-Hawking entropy. And I know we are running out of time, so just I will do my best to breeze through it, and if you have any questions, I can go into it more. Safehouse solutions have what I call the causality argument, where basically they say, the black hole interior is disconnected from the rest of the space-time, so only the horizon, only the surface system can mediate thermal contact with other thermodynamic systems, and that they take to be the most important criterion for universality. So the interior of the black hole can have as many states as you like. It can have an expanding universe inside, it doesn't really matter. And it may seem like this is an outdated position, but actually, if you just look at these dates, there are people still coming up with such proposals. So I just want to put pressure on the idea that, black hole complementarity and, entanglement wedge reconstruction, that these are really the only game in town. That's not quite true. And then on the other hand, evacuation solutions ascribe to the holographic principle, where Bekenstein-Hawking entropy, is a measure over everything there is to the black hole. And now we have a revisionary connection because it seems like the most amount of, information storage capacity a black hole has is bounded by the area of its horizon. And once you do that, you're going to have non-localizable degrees of freedom. And this is where, the gauge gravity dualities come into play, ADS-CFD correspondence, and why these proposals have used a lot of those tools in their work. And again, if you look at the dates, of course, this is, pretty prominent up until present day. So the difference in between these two is that Safehouse solutions say, yes, Hawking's curve was absolutely right. Hawking radiation can, have unbounded growth in entropy, but that's because Bekenstein-Hawking entropy is not all there is to the black hole. It just tells you what the surface system of the black hole is made of. The interior can have as much storage capacity as you want. And basically they say if Schrodinger's cat jumps into a black hole, its information will stay in the black hole. And then on the other hand, you have evacuation solutions where they say in purple here, the entanglement entropy between the black hole and the radiation, that's going to go up, but then it's going to come down because eventually the black hole is going to get too small and it's going to run out of degrees of freedom to purify the radiation. So this is the infamous page curve, which I'm sure a lot of you have seen. And they say that if Schrodinger's cat jumps into a black hole, its information is definitely going to come out in the radiation after the page time when the black hole's entropy coincides with the entanglement entropy. Okay, so this is basically an internal constraint because we don't really know based on other theories which interpretation we should go with. And I think more work needs to be done so that we can definitively say that either the causality argument or the holographic principle, they satisfy the universality argument, more compellingly, and then we need to establish, based on which criteria that I listed earlier, do they do a better job of establishing black holes as thermodynamic systems? So just to end, I will give you this quote by Bekenstein. 3 intricately related issues have characterized black hole thermodynamics for the better part of 2 decades. The meaning of black hole entropy, the mechanism behind the operation of the generalized second law, and the information loss paradox, or the information loss puzzle. The 3 issues are actually one in the sense that when people find out how to fundamentally resolve one of them, they will have resolved. Thank you.
Okay, so few questions. Would you like to field your own?
Oh, I can field.
No worries. I'll just chime in later.
Yeah, I'm kind of intrigued by this Planck-sized remnant
Yeah.
that can hold arbitrary amounts of information. I mean, it's okay to just state it, but is there an actual working model that does it?
So I had indicated in an earlier slide 2 recent proposals. One is by Alejandro Perez. So his proposal is that it's actually a massless remnant because after evaporation, you're just left with Minkowski spacetime. But he argues that the geometry is compatible with an infinite number of states based on the combinations of the Planckian degrees of freedom and loop quantum gravity. So there's an infinite degeneracy there. There are other bag of hole geometry, sort of bag of gold geometry proposals where the interior is its own universe essentially, and how they stabilize the surface system so that it stops evaporating. They think you can use a generalized uncertainty principle where the delta X and the delta omega, let's say, in terms of the frequencies, the delta X is can't go any smaller than the Planck length. And so they use that as an argument to say why the black hole would not actually evaporate to zero mass or have the event horizon completely disappear. So there are some proposals. Rovelli himself, he has done calculations of the volume of the interior, and he argues that if you calculate based on different Cauchy surfaces that get closer and closer to the singularity classically, the interior volume is actually expanding. So yeah, just to give you a sense, people have thought about this and tried to make it work, and their arguments are that these are not particles. You can't use particle physics to understand these remnants, even though they look like particles, and so they're just going to have completely radically new physics and how they interact with what we think of as ordinary matter. Yeah.
Okay, sorry if you already covered this, but are you thinking about your bare desiderata as like ruling out various proposals or giving them a direction to go into? And if the former, could you say more about?
Absolutely. So the bare desiderata, right as you said, is not ruling out proposals yet. It's giving them a direction to go. So these are external constraints that minimally any proposal to be considered a contender in this whole discourse, they have to at least meet the bare desiderata. And then it's the holistic desiderata where once we can, compare, and that's where the work needs to be done, compare the Safehouse and evacuation solutions and hopefully come to an agreement that, one or the other does a better job of making black holes thermodynamic systems such that they're continuous with familiar thermodynamic systems, then we can just completely slash one category and the remaining category would be part of the holistic desiderata.
So, okay, so for now, they're guiding principles that each of these should fulfill.
Right.
Are there ways in which you could flesh out what it looks like to start to fulfill these principles, like for one of the proposals or something?
Sure. So let me see if I can just go to where I have the bare desiderata. So there's been a lot of debate whether firewalls actually fulfill the bare desiderata or not. And if they don't, then that would be, a derivative level paradox, right? It's only for the evacuation solutions that try to say Hawking radiation is all that's left. But the worry is that they violate number 4, that you can't use the tools we thought worked well near the event horizon or outside the event horizon, because the event horizon classically is supposed to be a global feature of space-time. It's locally indiscernible, and that's why we say that the equivalence principle should presumably hold there. But if you have really, really high energy densities, and I won't be able to tell you exactly why we have high energy densities, but the idea is that to get information out in the radiation, you have to sever the entanglement across the horizon between the interior and the exterior. And what that does is that leads to very high energy densities such that it's a firewall and you get incinerated. So no matter what reference frame you're talking about, even an infalling object in its own reference frame, where classically it would have never noticed it was entering a black hole, now very much feel something and can locally discern the event horizon. So people think that's incoherent and that it's really undermining predecessor theories where, we expected them to work well. Other people say, well, we don't really know, and that's why I was careful to say at most up to a Planck scale cutoff, what the boundaries of our current theories are. So yes, general relativity predicts the existence of black holes with the event horizons, and we can choose coordinates such that we think we have physics of the interior until we get to the singularity. But maybe it's not just the near singularity region that needs to be revised by quantum gravity. Maybe it's all the way up to the event horizon. And so that's why it's contentious. For example, what it means to satisfy number 4 or number 6. Right? Effective theories are recovered as limiting cases. To do that, you need to set boundary conditions. What are the boundaries?
I had a question as well.
Yeah.
So you mentioned in passing that you can compute, for example, the entropy of the horizon, and it's just a quasi-local thing on the horizon. Versus, is it actually counting the degrees of freedom at the horizon versus its interior? So I think this is something what you said. So if you had, let's say, a non-vacuum solution where you had matter in the interior, there's a solution to classical Einstein equations, etc. Can you actually compute entropy inside the horizon as well? Is there a calculation that people have done so as to then say that, okay, this is a quasi-local quantity, like the Hawking mass or something like that?
So I don't think anyone would take that calculation to be physically meaningful insofar as we want. So for example, if we think of Bekenstein-Hawking entropy as holographic, right? It's a measure over all black hole degrees of freedom. But that's never calculated by just, taking the brute interior, because the interior can't be in thermodynamic equilibrium. Things are converging to the singularity. So what they do instead is they reconstruct interior degrees of freedom on what's called the stretched horizon. So they move to another reference frame where if you are an exterior stationary observer, you can say, okay, well, nothing crosses the event horizon anyway in my frame because of infinite time dilation. So why not impose a boundary condition at the event horizon, excise the exterior, and rewrite everything in terms of things that get frozen near the horizon. So they call that the stretched horizon. This is the membrane paradigm. And now in that setup, it's much easier to think of this viscous conducting membrane that can thermalize systems with which it comes into contact. And that's often approximated with a conformal field theory in the ADS-CFT correspondence. So if you can do that calculation by the duality, then you say, that's the same entropy as if it were the black hole interior. So as far as I know, both camps do agree that really only the surface system can actually be conceptualized as being thermodynamic, but now the physical interpretation of that for Safehouse solutions, no, that's literally the only thermodynamic system of a black hole. But for evacuation solutions, that's actually dual to the interior, and that's why you don't actually localize the degrees of freedom.
We started a bit late, so if there's any final questions, you can still take a few, but are there questions?
Don't we have to set up for the next?
11, I think.
Okay.
So I think I interpreted Prashant's question a little different,
Okay.
or maybe it's a different question. There are these regular black hole solutions that don't have a singularity at all. And you have to fiddle with some equation of state, do something. But you can make these solutions, and presumably you can come up with a theory where you collapse and make this guy. So it's a well-defined physical process. So could one take an object like this and actually count how much entropy is there in the interior volume is that in any way compatible with the area? Is there an ADS, CFT or whatever, I don't know what to call it, but some correspondence between volume and area for these guys, which I think since they don't have a singularity, are probably, easier to actually compute stuff.
Yeah.
Also, I'll just add that these are the matter there inside the horizon is also in a static configuration, because somehow the equation of state is such that there's negative pressure. It satisfies the energy conditions, so it's still static. There's no focusing happening. So, is there a notion of thermodynamic equilibrium in these sorts of systems that you can use to then check whether it's counting all the degrees of freedom inside or it's just quasi-local
Yeah.
in that sense?
So the only proposal that I'm aware of that has taken advantage of this situation is the Fuzzball proposal by Samir Mathur, where he looks at extremal black holes that are formed without event horizons or singularities. So these are fine-tuned solutions, and what he does is he then perturbs them to calculate the entropy. So his approach at least has been to say, and this is why I put Fuzzballs in purple, it's kind of straddling, both positions. What he says is that a classical space-time never actually forms behind the event horizon. And so you have these extremal black holes where you just have the surface system, that's all there is, that's what they have in common with the Safehouse solutions. But now, because you don't have to, worry about locality or any causal barrier, all of the radiation and the information gets out without a problem, and that's what they have in common with the evacuation solutions. And they have this notion called fuzzball complementarity, where if you have an infalling object, it should experience something akin to a classical free fall into the interior, but what's actually happening is that it's riding the surface system until its own constituents, as if it were experiencing tidal forces, rip apart and become part of the fuzzball. So I know that's not as satisfying.
It doesn't have a horizon.
Exactly.
Whereas the objects
Yeah.
Prashant is talking about, they
Has a
have a
horizon.
horizon but no singularity.
Right. So I guess that depends on the curvature inside. I mean, if the singularity is the only distinction between the two cases, then I think the arguments against thermodynamic equilibrium might still hold in terms of the tidal forces and the convergence towards high curvature regimes, but I'm not sure, and that's something that would be interesting to look into.
Do you have a preference among these nine alternatives?
I'm leaning towards the evacuation solutions, so towards a holographic interpretation of black holes. And the reason is,
So where is that in the nine?
so basically all of these, the most recent one is wormholes and islands. And I think that's a really interesting proposal, because they get to eat their cake, have their cake and eat it too. What they want to say is, in one reference frame or basis, the late time radiation is entangled with a remnant or black hole interior, but in another basis or a reference frame, it's not, and you just have radiation left that's entangled with each other. But here's my preliminary thoughts on comparing the two. I think the holographic camp, they do a better job with defining thermality, because when the black hole is large, it can act as the environment for the radiation, to be its heat bath. But when it gets too small, it can't do that anymore. And I think it's actually good that it stops being exactly thermal after the peak time. And I also think that they use the statistical ensembles more consistently. Now, of course, we don't know if there's a paradox there. If the recent work has basically shown that in semi-classical gravity, you don't have fireballs necessarily, that's huge progress. So I'm definitely leaning towards them. But one thing Safehouse solutions do is that they have a better account of black holes actually making thermal contact with other systems. Because here, if you have a dual description, it's not really clear, in what sense a black hole is coupling with something else that's dynamically meaningful, right? You can go to one description or the other. So physical equivalence is a thorn that very much needs to be worked out.
Good, thank you.
Okay, so everyone, thank you. And thanks to everyone on Zoom as well.